and then I'm gonna just do the intro. Hey, hello guys. Welcome to the second installment of a video series I've chosen to call D.U.M.B, or Decisively Understanding My Botherations. It's me picking apart video games with math and science. That's what it is. And in this video, I'm picking apart Outer Wilds a little bit, because I was curious, like, would I actually be able to even leave the planet? Because I was just thinking, like, hey, would the escape velocity be too strong, or would the thrusters just not be enough? And so I wanted to look into it, and so I looked into it, and that's what we're here for. So to start everything off, we need to know the escape velocity equation. The escape velocity equation is VE equals the square root of 2gm over r. G is our gravitational constant of the universe, and G is also a very much known number that you can just look up, so there's no work that has to be done for that. M is our planetary mass of said planet, and we'll get to that in a moment. And our R is our radius of said planet, and in this case the planet is Timber Hearth. So the very first thing we need to do for anything with a video game is be able to put pixels to an actual form of number, like meters, right? So that's called pixel measurements, and that's what we're doing. In this case, what we need to do is find a real-world object that is equivalent to a video game object. And in this case, I found a barrel. This barrel happens to be a hogshead barrel, which measures 1.22 meters in height in real life, and it's 137 pixels in the game. Now, keep in mind, everything has to be done with scaling in mind. So I'm taking this, everything will be taken with 10 meters of distance between our character and the object, or 10 kilometers, because we can scale from 10 meters to 10 kilometers rather easily. Just multiply by 1,000. For scaling in this case, we can multiply by 1,000. But we have to do that because if we're too close, the object is going to take up more pixels than if we were further away. So 1.22 meters in height in real life and 137 pixels from 10 meters. We divide our 1.22 by our 137, and we get a single pixel being equal to 0.0089051095 meters. And so since we have what one pixel is equal to, we can solve for the planetary mass now. How are we going to do that? That's actually not that hard. It's the planetary mass equation, which is acceleration times r squared divided by g. Once again, big G is g, there's gravitational constant. Our a in this case is acceleration due to gravity, and our r is radius of the planet. Hey, quickly interjecting, I misspoke when I said r is equal to the radius of the planet in this case. R in the planetary mass equation is equal to the radius between the two objects we're using. So in this case being our character and our mass and the actual planet itself. So that's what R is. See ya. So we're going to solve for A first. A is equivalent to Fg equals ma, or force of gravity equals mass times acceleration. And so we need obviously a mass to be able to solve for the gravity. So we're going to find the mass of our character. To find the mass of our character, we're going to measure him, and so I put him up to our makeshift ruler, which is this sign, because we know how tall, we know that standing at that red line there, it's 190 pixels, and so our character stands at 190 pixels, so we can convert that to an actual height of 1.69 meters, and the range of weight for someone who's 1.69 meters tall is 114 to 144 pounds, and so we'll take the median of 129, convert it to an actual unit that we can use called kilograms, and that gives us 58.51228022 kilograms. So we now know our mass of our character alone, but there's a spacesuit attached to him. The average spacesuit typically weighs 127 kilograms, so we get a total mass of 185.51338022 kilograms. And so we know our mass, and now we need to find our acceleration. To find acceleration, we just need to use one of the many equations of acceleration, and in this case, we're going to be using the distance traveled for acceleration. That equation is a equals 2 times delta d minus vi times delta t over delta t squared. Delta is just a term for your final and minus your initial. Most of the time, it's just there, but you don't actually need to use it, and it doesn't matter that much in this case. We could just say D. Nonetheless, delta D is our distance, VI is our velocity initial, delta T is our time, and so to solve for this, we're just gonna need to jump. And so I jumped from 4 meters, timed it at the peak of the height to the bottom of the height of the jump, being 0.33 seconds, and so our initial velocity from the peak is 0. So we plug in all our numbers, our 4 meters minus our 0 times our time of 0.33, and we get an acceleration of 73.46 meters per second squared. So we have our mass and our acceleration, and so we plug them into our original equation of Fg to get an acceleration due to gravity of 13,627.5646 meters per second squared. So now that we have our acceleration due to gravity, we can go back to our planetary mass equation and solve for the radius. The radius is rather simple in this case, as it's just the radius between two objects. In this case, it's the radius between Hearth, from the center of Hearth to our character in the jump. And so we're just gonna fly out 10 kilometers, because it's a space game, conveniently, to get our radius. So we'll fly out 10 kilometers, take a photo of it, like we just did. We have that photo. We measure it out to be 45 pixels in diameter, meaning it's 22.5 pixels in radius, and so we can convert that into a planetary radius of 200,364.9634, because we can scale from the 10 meter ratio to a 10 kilometer ratio. And then we can add on our 4 meters from our jump to get a radius of 200,368.9634 meters. Big G is just our gravitational constant, which is 6.6743 times 10 to the negative 11 meters per something. I don't know the units. It doesn't really matter. We're going to plug everything into our planetary mass, plug in our G, our A, and our M, and we get a planetary mass of 44 sextillion, 188 quintillion, 179 quadrillion, and 30 trillion kilograms. So the final part is our initial equation, escape velocity. We're back to that. Our escape velocity is the square root of 2gm over r. We know our g, we know our m, and we know our r. So we can plug it all in. Our r in this case is without the 4 meters added on. I know, it's gonna make such a big difference. And when we plug them all in, we get a final escape velocity of 5,425.698864 meters a second, or 12,136.94269863994 miles per hour. And so that's actually really good, because the Earth's escape velocity is 11,176 meters per second, so it's near double. It's about double the escape velocity of our in-game escape velocity. And the mass of Earth is 5 septillion, 972 sextillion kilograms. So one, that actually makes some sense that something with a much lower mass would have such a lower escape velocity than Earth. And it makes sense that we could actually escape it with our rocket ship in the game. So it all works out actually rather well. However, the planet actually being able to exist in this solar system of perfectly circular motion, not so much. But that's for another video, which I will have out sometime between now and later. It'll be out eventually, but we know that we can escape the planet, which is great, because at least that one area works. The rest of it, not so much. It would not be a good, you wouldn't want to live in this solar system. But that's the whole thing, that's everything. Thank you all for watching. I hope you enjoyed nonsense breaking down of a video game. I enjoyed it, and I hope to do more of this. Thank you all for watching. Have a great rest of your day. Bye.